section 10.1. Today we're going to discuss the concept of correlation. And sometimes in real applications, the real life applications, you have two quantities that are linked or associated with each other, not in a cause and effect form relation. It's not a cause and effect, meaning one variable causes the other variable, but they coexist, they are related. Like, for example, smoking and a lung disease. There is a kind of relation between the two, and we call that relation correlation. So correlation is a relation that exists between two variables, but it is not of the cause and effect, meaning if you smoke doesn't mean for sure the result is a lung disease. There is no cause. If this happens, then this will happen. No, but there is a relation, a correlation or association between the two. And our goal in this course is to analyze that relation, study the relation, measure it, identify, see whether there is a correlation or not, and so on. So we are not trying to establish a cause and effect. If something happens, then this will happen. No, but we are trying to establish and determine whether there is an association or correlation between two variables. So here's my definition. A correlation exists between two variables when the values of one variable are somehow associated with the values of the other variable. This is what we're going to be concerned with in this section. Correlation does not mean cause and effect. It means just some type of relation. If one variable, the values of one variable increase, the other variable will also increase, the values of the other variable will also increase or decrease. Somehow there is a connection or a link between the two variables. But this concept of correlation is broad. In our course, we're gonna discuss one specific type of correlation, which is the linear correlation. So we're not gonna talk about different types or discuss different relations. We're gonna focus on one kind of correlation, which is linear correlation. Definition. A linear correlation exists between two variables when there is a correlation and the plotted points of paired data in a pattern, result, the plotted points of paired data result in a pattern that can be approximated by a straight line. All right, so when we discuss correlation between two variables, we have one specific type here that we're going to discuss, which is linear correlation, in which the relation between the two variables can be represented by a straight line. And that line can have a positive slope or negative slope, but it can be represented by a straight line, so we call it a linear relation or linear correlation between the variables. Okay, so let me explain, guys, a little bit more about this concept of linear correlation. When we collect sample data, our sample data is going to look like a set of order pairs. X1, Y1, X2, Y2, X3, Y3, and so on. Xn, Yn. Right? The first number in each pair is a value of the first variable. The second number is a value of the second variable. So our sample data is going to look like this, or it sometimes is going to be given in a table format, like this. X and Y. All right. So X could be, for example, a measurement, for example, let's say for the amount of or the number of cigarettes smoked per day, and Y could be, for example, the amount of a specific, chemical specific substance in the blood. So it's both of these are measurements, and you will have a set of order pairs, X1, Y1, X2, Y2, and so on. Okay. Or for example, X is the number of hours you study, and Y is your test score. So we have this sample data. Now, when you take this sample data and you plot these order pairs, you're going to get points. You're going to plot points. Here's the x-axis. This is the y-axis. The x variable is always the independent variable. The independent variable. Is always labeled or called the independent variable. So for example, study time in hours. Amount you spend studying, and y is the dependent variable, which is your test score. We can study this relation between the two variables. We can study the relation between how much time you put studying for a test and the result, the test score. So we always put the x values, which are the values of the independent variable, on the horizontal axis, and we put the values of the y variable, the dependent variable, on the vertical axis. Now, sometimes we notice the following. When we plot these ordered pairs, we notice that these ordered pairs will give me this type of pattern. Whereas we go to the right, as x increases, y will also increase. So this is what we call a scatter plot, where each point represents an ordered pair in the sample. So this point, for example, represents the first order pair x1, y1. Another pair here, another point for, let's say, x3, y3, and so on. So each point represents a pair of data values. Okay. Now, when we study relation between variables, sometimes, as I said, we end up seeing, we see after we get the scatter plot, we see this pattern, and this pattern can be represented by a straight line. You can see here there is a line. I can draw a line that goes through most of these points, and it goes through most of these points and very close to the rest of the points. So this tells me right away that there is a possibility for a positive linear correlation between these two variables. Positive linear correlation. And this is just by looking at the plot. I didn't do any calculations yet. From the scatter plot, there is a possibility, that these two variables are linearly correlated to each other. That if one of the x variable increases, the y variable will increase. If the x variable decreases, the y variable will decrease. So this is what I mean by a positive linear correlation. Also, we call it positive because the line has a positive slope. Remember, if the line rises like this, then the slope of the line is positive. Slope is greater than 0. Okay. There is another possibility, which is the negative linear correlation. In this case, if we plot our sample data, we will notice that, so again here, this is our x variable, the independent variable. This is y variable. If we take our sample data, these sample order pairs, and we plot them, we get a pattern that like this. And you can see here, I can draw a line that goes through some of these points and close to the other ones. I can represent this plot with this straight line. In this plot here, you can see that when we go to the right, as x increases, y will decrease. So this is called a negative linear correlation between x and y. Reason we labeled it negative, because if x increases, y will decrease. It's like an inverse relation. And also because the line has a negative slope. Okay. So in our discussion today, we're gonna focus on this type of relation, positive. We wanna determine whether the relation is positive or negative, positive linear or negative linear. And we're gonna measure the strength, how close these two variables are related to each other. You wanna measure the strength of the correlation. Okay, any questions so far? I want to show you guys some computer generated scatter plots. So after looking or after plotting these statistical plots, these are called scatter plots. After looking at these scatter plots, we can predict, by looking at the pattern and the plot, we can predict that the relation is linear, positive linear, or negative linear. And our next step is to measure this linear relation between the two variables. Okay, so measuring, we're going to measure the strength of the linear correlation with R. R is called the linear correlation coefficient. We're going to talk about this in a minute. This is a very important statistic, R, which is called the correlation or the linear correlation coefficient. The linear correlation coefficient is a number that we're going to calculate that measures the strength of the linearity of the linear relation between the independent variable and the dependent variable. Again, we are looking at these scatter plots. If we enter our data into a computer program or a statistical program, we gonna get a value for R, the correlation coefficient. Now, for example, look at this first plot here. You can see that we can easily identify a linear relation here. There's this, clearly a straight line that goes through the points. And when we enter these points in our program, we the program gives us this value. See how positive value here, 0.859, a positive value. I will talk about the values of the correlation coefficient in a second. The second one, the other plot that you see here, negative, there's a negative line that can be drawn. Look at the correlation coefficient here that is given by the program. It is negative 0.971. This next plot, you see how the points are scattered everywhere. We do not see any pattern. Look how small the value of R is, very almost 0.074. This next one here, there is a nonlinear relation between the two variables, which means we start with a positive relation. As X increases, Y will increase, but somehow at certain point, if X increases, Y is going to start to decrease. So this is a nonlinear relationship. And if we calculate the linear correlation coefficient, the value of the correlation coefficient is very small, right? It's very small because this value only measures the linear relation, not other types of relations between the variables. Okay, so if the relation from the beginning is linear, then we calculate R and measure that linear relation. Okay, so now let me talk about this variable. The linear correlation coefficient has a range. Its values range from -1 to +1. Here's the 0. This is the range of R, the correlation coefficient. As the value of R gets closer and closer to 1, the relation between the two variables become more and more, or stronger and stronger, linear. So if R, let's say, is 0.9, then when we look at the scatter plot, we clearly see the linear relation between the two variables. We see almost like a perfect straight line, right? As the value of R gets closer and closer to 1. The closer to 1, again, the stronger the positive linear relation between the two. As R approaches the middle, as R approaches 0, let's say, for example, if I pick here, let's say R is 0.2, then if I look at the scatter plot, I see we will see a pattern that is almost like a random pattern. Like that. We do not see this a clear linear relation. As R approaches -1, the relation between X and Y become more and more linear, but in the negative direction, meaning that if you look at the scatter plot, let's say here R is -0.95, for example, then our scatter plot will look pretty much like this one here. Clear, linear relation that can be represented by a line with negative slope. Okay. So the more positive, the closer we are to 1, the stronger the real relation, positive, linear. The closer the value of R to -1, the stronger the negative linear relation between the two variables. Okay, any questions? R, when R is very close to 0, almost no linear correlation between the variables. Okay. Any questions, guys, on this? So we talked about the range of R. Now we're gonna calculate the correlation coefficient. Calculating the linear correlation coefficient. Again, remember our calculation is going to be based on a set of order pairs, right? Our sample data is a set of order pairs. X and Y n. There is a formula, mathematical formula that we're going to use, or we can use to calculate R by hand calculations. Here is the formula. You can see that this formula is not easy to use. It takes some time, a lot of work to hand calculate and get the value of the correlation coefficient. I just want to talk about the terms that we see in our formula for calculating R. I'm not going to ask you to use it on the test. I know it takes a lot of time to calculate using the formula. I will show you in a minute how you can enter your X and Y values into your calculator and find the correlation coefficient. But I just wanted to show you guys here that your calculator is programmed to evaluate this formula here. Look at the first term. This is the number of pairs. This is the sum of the product of X times Y. You take each X value, multiply it by its corresponding value, and add the products. And this is the sum of the X values, sum of the Y values. This is the sum of the squared values of X. This is the sum of the X values squared, and so on. It requires, time to evaluate the correlation coefficient. So usually this formula is programmed, and you can easily get it using a statistical software or a TI calculator. Okay. So let me show you guys how we're going to get the value of the correlation coefficient for this sample. Example. Find the value of R, the linear correlation coefficient. I'm going to present my values, data values like this in this table. So 5 and 6, 6, 9, 4, 3, 4 and 2, 5 and 11. Right? X values on top, Y values, the corresponding Y values in the bottom. So this column here, you can see, is an ordered pair. So the 5 and 6 are together. The 5 and 6 together. All right. So let me share my calculator with you so I can see how we're going to get the value of R from the table. All right, so press the stat key. 4. We want to clear 2 columns in our calculator memory. So we're going to clear L1. And then we're going to press the stat key again. 4. And clear L2. And then the stat key again, press it. And then 1 for edit. And now enter the X values into L1. 5. 6. 4. 4. 5. And then move your cursor to the next column and enter the corresponding Y values. 6, 9, 3, 2, 11. Make sure that you enter the pairs correctly. 5 with 6, 6 with 9, 4 with 3, 4 with 2, and 5 with 11. So we entered our pairs, X values in L1, the independent variable values into L1, and the dependent variable into L2. Now press the stat key, move to the right, calculate, and then scroll down to let's see where it is, 8. Uh, 8, which is linear regression model. Enter. The calculator is going to want you to confirm your X list is an L1, yes. Move down. Y list is an L2, yes. Frequency list, there's no frequency list, skip that. Skip the next line. And then calculate. Actually, guys, this one, I made a mistake. This one gives you only the equation. I'm sorry about this. Go back to stat again, calculate. I think the, where is it? It's a little bit different from, it's 4 and 8 are the same. Hold on. Let's go to the virtual one is a little bit different from the one I have. Let me check here, linear regression, enter. Calculate. Where is the correlation coefficient here? That's weird. Guys, your calculator should have, the actual calculator has the correlation coefficient. Apologize, guys. I found it. It should be under tests. Apologize for this. It is under tests. Please select linear regression t-test. Linear regression t-test. Select that. L1. Yes. L2. Don't worry about the symbols here that we have. Just go straight to calculate. Excellent. So here it is. This one has the regression equation, and here it is at the bottom, 0.794. 0.795. If you round to 3 decimal places, 0.795. Right? Any questions, guys? I'm sorry again. I'm going to go this over one more time. I selected the wrong function here. Again, go to tests and then go down to linear regression t-test. Calculate. .795. Are we all okay, guys, with this? Questions? Calculator questions? Okay. So let's me go back. So again, just to summarize, X goes into L1, Y goes into L2, and then press the stat key, go to tests, and then from tests, go down to one, where is it? Option F, which is linear regression. T-test. Okay. R is 0.795. You always round to 3 decimal places. Okay. All right, so after finding the value of R from your sample data, from the sample order pairs, you need to compare your R value from the sample. This is called the R test value that you get from the sample, you need to compare it to R critical. We have a table that gives us, depending on the number of pairs we have, it gives us what we call the critical correlation coefficient value. Let me show you this table here. It should be in your book here. On page 692. This table will be provided for you with the test tomorrow. It's going to be part of your test. As this table is used to get the critical value of correlation coefficient for a specific number of ordered pairs. So in our example that we're working on, we have what? We have 1, 2, 3, 4, 5 ordered pairs. So that means N is 5. Now, let's assume that we are using a 0.05 significance level. Let's say we are studying our sample data and we want to know whether there is a linear correlation or not between the variables, and we are doing our calculations based on the significance level of 0.05. In this case, if alpha is 0.05, and since we have 5 pairs, then the critical correlation coefficient is 0.878. 0.878. So we calculated from the sample, we calculated our correlation coefficient 0.795. Now we're going to say, we're going to draw this line here. The range of R, -1, +1. Our critical R, critical value is 0.878. Okay, 0.878. Our test value that we got from the sample is 0.797, which is below R critical. R-test. Now, since R-test did not fall between R critical and 1, R-test did not exceed the critical value. Statistically, we gonna say that there is no linear correlation between the variables, between the X and the Y variables. R-test is not between R critical and 1. Based on this standardized table for critical values of correlation coefficient, we can confirm and say there is no linear correlation between the two variables, period. In order to establish a linear correlation between the two variables, and we're talking about positive value, if R-test is positive, we're trying to establish a positive linear correlation. In order to establish that, our test value must be greater than R critical, and of course less than 1, between R critical and 1. Since it is not in this case, then we say there is no linear correlation between the two variables. Okay, based on the assumption again that alpha is 0.05. If you take the other column, the 0.01, the critical value is even higher. See here, alpha is 0.01. Look at the critical value is even higher than the 0.05 value. So whether alpha is 0.05, in this case 0.01, there is no linear correlation between the two variables. This is how, guys, we use our sample data to establish this relation to, to confirm or to say that there is either linear correlation or no linear correlation between the two. Okay. Any questions? Question from Jason: if we cannot find the n value or over the 100, then we choose yes, absolutely. Usually with correlation, when you study the relation between correlation, you should be able to usually have a small number of paired data, and you should be able to use the correlation coefficient table. If not, then if you have large number of values, then of course you round to 100. I think it's the last one is 100, yes. If it's greater than 100. Let's say you have 27 pairs of sample data. There is no 27, then you will choose the closest number, which is 25. All right? Let's say you have 39, you always choose the closest number, yes. Okay. Let's take a look at another example. Question again from Jason, what about 55? Let me see. 55, which is exactly in the middle, I usually choose the lower value, the stricter value, the 50, instead of the 60. The larger value, the larger critical value, uh, that corresponds with 50 pairs, 0.279. Okay. I have another example I want to show you here. Example, calculate R the linear correlation coefficient and determine whether there is a linear correlation between the two variables. Let me add another pair. All right. I have these values. Let's go ahead and enter those values into the calculator and find the correlation coefficient test value, R test. So we're going to enter our X values. Make sure you clear L1, L2. 2, enter. 1, enter. 3, 5, 4, 6. 2, 1, 3, 4, 5, 4, 6. And then the Y values. -6, 0, -8, -9, -5, and -7. I'm checking my 2 and -6, 1 and 0, 3 and -8, 5 and -9, 4 and -5, 6 and -7. Press the Stat key. Go to Tests. And go to Linear Regression t-test. Calculate. R test. Notice it is -0.687. You guys agree with that? Anyone got the same number? All right, excellent, thank you. All right, so now let's determine whether there is a linear correlation coefficient, a linear correlation or not between the variables. -1, 1. I have 1, 2, 3, 4, 5, 6 pairs. So I'm going to go to the table. I'm going to assume that alpha is again 0.05. Based on this possible in making a mistake, 5%, alpha is 0.05. I have now 6 pairs instead of 5. I'm going to get 0.811, but notice since my test value is negative, I'm going to put a negative sign for my critical value. The table gives you the absolute value, the positive value, but when you use it, you're going to say that R critical is negative. If your test value is negative, then your R critical is negative. Negative 0.811. So now, here's your R critical. Negative 0.811. And your test value is to the right of your critical value. All right, so our test is negative 0.687. Notice it does not fall, our test value does not fall in this interval between R critical and -1. It is not less than or more negative than R critical. It's not closer to -1 than R critical. So therefore, again, because of this test value did not exceed, is not more negative than R critical, then we can say again, no linear correlation between the two variables. Guys, linear correlation exists only if you have this case where here's your -1 and here's your R critical, and R test falls between them somewhere here in this section, R test. If it falls between these R critical and -1, then we can say there is linear correlation. But in our example here, this is not the case. So therefore, no linear correlation between the two variables. Jason, alpha value is always, yes, correct. On the test tomorrow, guys, I will give you the value of alpha. It's going to be either 0.05 or 0.01. You're going to use the table to get your R critical value based on the given value of alpha. All right. The next section, notice here in the first section, we talked about the concept of correlation. We talked about linear correlation, how to find the correlation coefficient, and how to determine whether there is a linear correlation between the variables or not. Now, in the next section, 10.2, we're going to talk about the linear regression equation. The linear regression equation.
Bye. Bye.
After establishing or after showing that there is a linear correlation between the two variables, now we're going to find the equation of the line that represents the sample, the data. Again, remember, we have a scatter plot, X and Y, and the plot looks like this. And we established that there is a linear correlation between the two. Now we're going to talk about the line that, or the equation of the line that represents our sample data. All right, so we have a collection of paired sample data, This line that you see here, guys, is called the regression line. Or some other books, they call it the line of best fit. Line of best fit. It is a straight line, and it is the best line that represents our scatter plot, the scatter plot of the data. All right, this is the best fitting. Regression line is the best line that is, you know, there's some mathematical calculations algorithm that we apply to get this line, that the best fitting line, or the line that represents our sample data. And the equation of this line is called the regression equation. The regression equation which has a general form y hat equals let me give you the equation that we have here, equals a plus bx this equation expresses a relationship between x, the independent variable, and y hat, which is the predicted value of the dependent variable. Okay. So this is this equation is going to help us predict the value of the dependent variable, the y value, based on a given value. It is used for predicting the response, the value of the dependent variable. Because now this line is the best line, or the line that represents our data, so we can use it to predict the dependent variable. Okay. Let me show you how we're gonna use the regression equation. Example. Consider the following pairs of sample data. I'm going to give you sample data, X, Y, one, 1.8, 2, 2.7, 4, 4.5, and the Y values 2.5, 3, 3.1, 3.9, 5, 5.7. First part, find the correlation coefficient. Second part, determine whether there is a linear correlation between X and Y. C, find Y, sorry, before that, forgot. Find the regression equation. D, predict the Y value when X is let's say 2.1. Predict the Y value when X is 3, and predict the Y value when X is 8. All right. So go ahead and enter, guys, the X values into L1 and the Y values into L2 and find the correlation coefficient. So 1, 1.8, 0.7, and then enter the y values. Stat key, go to tests. Linear regression t-test. Calculate. The linear correlation coefficient, in this case, based on the sample data, is 0.994. I got this number again from L1 and L2. I pressed the stat, went to tests, linear regression t-test. Linear regression t-test, yes. Anyone would like to confirm? 0.994. All right, thank you guys. So 0.994. Second part. Determine whether there is a linear correlation between X and Y. This depends on now R critical. R critical. Again, I keep forgetting to give you the value of alpha. Let me put it here. Alpha is 0.05. All right, based on alpha of 0.05 and number of pairs. How many pairs we have? 2, 4, 6. N is 6. Alpha is 0.05. 0.811. So R critical, 0.811. Our test value is to the right of R critical, so it's greater than R critical, less than 1, of course, R test. It falls in the region between R critical, in the interval between R critical and 1. So now we can say there is linear correlation between the variables. We got our test, we got our critical, we compare them, we established, now we say that there is linear correlation between the variables. In the next part, guys, if you go back to the calculator, on the top, when you go to linear regression t-test, you will see an equation, y equals a plus by, y equals a plus bx. And then if you scroll down, you will see a and b. So take the values of a and p and put them in the equation. 3 decimal places. Y equals 1.405 plus b, which is 0.923x. And then put y hat. because in this case, y is a calculated value. It's a predicted value, not an observed value. Y is an observed value. If you're not in this, y by itself is an observed value that is in the table. But now we're calculating y, so this is called the predicted value. So we label it y hat, or we use y hat for that value. Okay, we got our regression equation. So we first established that there is a linear correlation between the two variables. Now this equation is a valid equation. We showed that it is valid because there is a linear relation between them. This is the equation of the regression line, the line that best fit the data. Now we're going to use it in the next part. Predict the y value when x is 2.1. All you need to do is just plug in the x value. We're going to say when x is 2.1, then the predicted value of y, which we call it y hat, is 1.405 plus 0.923 times x, which is 2.1, and then we calculate 1.405 plus 0.923 times 2.1. That will give me 3.3433. Y hat. Next part, predict the value. Before I go to the next part, guys, notice that in this part here, x is 2.1. And if you look at our data values, 2.1 is within our range of data values. See here, 2.1 is between these two data values, 2 and 2.7. When our x value is within our range, then we can use our regression equation to predict. Because remember, this regression equation represents the line that represents this data set. So when we use it to predict the y value, our x value must be within the range of our data values. It cannot be outside the range. 2.1 is within, so no problem. We can use that regression equation to predict. The next part, which is what x value here, predict the y value when x is 3. 3 is also within the range because our values go to 4.5. So again, I'm going to say here when x is 3, then the predicted value of y hat is 1.405 plus 0.923 times 3. 1.405 plus 0.923 times 3. 4.174. Our regression equation is a good mathematical model for predicting the y variable for any x variable, for any x value that is within our sample data, within the range of our sample data. The next part, if you look carefully, guys, on the last part here, predict the y value when x is 8. What should I say, guys, here? X is 8. And look at the range of our sample data. X, 1, 1.8, 2, 2.7, 4, 4.5. Can I use the regression equation to predict the y value in this case? Can I use it? I cannot. Reason? Because this x value is not within the range of our sample data. Our linear equation is limited to only to the range of the data in the table. X equals 8, we need to collect more sample data. We need to get more ordered pairs to cover that X value here, 8. So here I'm going to say cannot find a predicted value for y since the given x value is outside the range of sample data. So do not give, in this case, a y value for this x value. This y value is going to be way different from the actual y value for this given x value. You have, as I said to you, have to increase your sample size. You have to take more sample pairs that cover this value of x in order to predict, this value. All right, so 2.1 was okay to predict, was within the values we have. The 3 is okay, but the 8 is not, so we cannot predict. All right, guys, any questions on prediction here using the regression equation? All right, this is what I wanted to share with you guys today.